Okay, so let's start. Last couple of lectures we were looking at different aspects of common emitter amplifier, and one of the remaining things is frequency response, a very important part. So far we've been analyzing amplifiers by saying that we are analyzing it in the mid frequency range, where the characteristics are independent of frequency. And as I've mentioned before, if we take any amplifier, a general characteristics of the amplifier with respect to frequency. Here we have plotted voltage gain versus frequency. A general feature is that the voltage gain drops at lower frequencies and drops at higher frequencies also. And in the middle, it's relatively constant here. So this is the mid-band frequency range. So not just the voltage gain. If I look at input resistance, that also will be a function of frequency. So input resistance for this amplifier, you can note that there's a region where it's varying with frequency, and then there's a region here which is independent, and then again it begins to vary with frequency here. So mid-band is a range where the amplifier's characteristics are insensitive to frequency, and we have seen that although we take a very simple case of sinusoid for analysis, I mean, one is really interested in amplifying a sinusoid. The signals are far more complex. An audio signal, we know that, would consist of anything between 20 hertz to maybe 20, 30 kilohertz. And therefore, we want these frequencies to be amplified. We don't want to distort the signal, amplify certain frequencies more than the others. And therefore, we would like our amplifier to operate in this range here, where its characteristics is independent of frequency. Obviously, it's of interest to know what is the range, what is the extent of this particular region here, why does it fall here, and we would like to calculate the 3 dB frequency here. If we plot gain in dB, then let's say the gain is whatever 40 dB, we would like to find out where does the gain go to 37 dB. So that marks the transition point, or that marks the edge beyond which the characteristics become frequency dependent. Similarly, we would like to know so that would give us the lower cutoff frequency. Similarly, we would like to know where does the gain fall from, let's say 40 dB to 37 dB on the higher side. That would give us the upper cutoff frequency here. So we define lower and upper cutoff frequencies in terms of the voltage gains plot as a function of frequency here. All right. So why does so we know that the amplifier's characteristics frequency dependent. Why does it vary with frequency? Well, the reasons are the capacitances that are there. I have these 3 capacitors are obvious. This capacitor required to couple the signal here. This required to couple the signal to the load. This is a bypass capacitor. We have 3 capacitors here. These are all external coupling and bypass capacitors. Whenever we have a capacitor along with the resistor will give rise to frequency dependent characteristics here. Apart from that, we have this transistor here, and we have seen that the transistor has C pi and C mu and substrate capacitances here. So all these internal transistor capacitances are also there, and they in combination with the resistors also give rise to frequency dependent behavior. So these are the sources, the external capacitors that are there and the internal transistor capacitances. If we look at you'll see it in a minute. If we analyze it, you'll find that the lower cutoff frequency, they arise because of the external capacitors that we have connected here. External coupling capacitors and the bypass capacitors. While the upper cutoff frequency, they arise due to transistors' internal capacitances. And there's a difference between their impact. The internal transistor capacitances, as you can see here, they cause transistors gain to reduce at higher frequencies, and the external causes it to decrease at lower frequencies. And the reason why this is lower and why this is higher has to do with the magnitude of the capacitors. The capacitors that you see here, you can see here 10 microfarad, 10 microfarad, 10 microfarad. These are large capacitors. And you know that any cutoff frequency is 1 by 2 pi times some capacitor and resistor here. So the 3 dB frequency is inversely proportional to capacitance. In the quiz, for example, you guys had to calculate the capacitances here of the transistor, and you know the transistor capacitances are depends on the kind of transistor, but in picofarads or even lower. Okay, in some cases it can be hundreds of picofarads as well. So you can see the difference in the range. These are in picofarads and these are in microfarads. So you can see at least a 3 to 4 orders of magnitude difference in the values of the capacitors that are there. And that causes this kind of a behavior here, that the upper cutoff frequency is at higher frequency resulting from small transistor capacitances. All right. Before we start to calculate these values here, these upper cutoff frequency and lower cutoff frequency, a little bit of background from your EE210, which I'll go very quickly. This is a circuit that you're all familiar with, an RC circuit, R and a C. When we take V0 by V in, we get what we call as a low frequency. It's called a low pass filter because it passes lower frequencies and attenuates higher frequencies. Okay, this circuit you can analyze in time domain and frequency domain. This is more of interest to us. And in the frequency domain, we can calculate the transfer function. We can calculate either using V0s by Vns, we can calculate and show this expression, simple expression here. We can substitute S equal to j omega. We get the transfer function here in terms of the frequency here, 1 over j omega RC. As I said, I'm just quickly going over it. We can take the magnitude. We can take the phase. And if we plot it out, what you can see is this is the plot of the magnitude. And similarly, I can plot the phase. If I plot the magnitude, this is how, well, at lower frequencies it's flat, and at higher frequencies it begins to drop. But it's more interesting to plot this not in the linear log domain, but more in terms of dB. And then we can see clearly here so that as it begins to drop, so it's this particular RC filter has 0 dB gain, and there's a frequency at which the gain or the RC filter's response falls by 3 dB. We call that the 3 dB frequency, and easy to show from this expression here that 3 dB frequency is 1 over 2 pi RC. Okay, so whatever is the R connected in series with the capacitor, that gives us the 3 dB frequency here. All right, so that's the 3 dB frequency of an RC, simple RC here. Okay, so all this should be familiar to you. All this magnitude response and the phase response and all that. All right, time domain, we don't normally encounter this in amplifiers because most of our signals are small signals here. But you know that if you excite your RC circuit by a step, then what you get is exponential charging and exponential discharge. And then you have all these, you can define as charging time and discharging time, rise time and the fall time, and they are all related to the RC time constant, which is also related to F3dB. Okay, so the two are related together. How much time does it take to charge? How much time does it take to discharge? Inversely related to F3dB. All right, so that was low pass. High pass is where you interchange resistors and capacitors, and then you know that low frequencies will be blocked by the capacitor. High frequencies, the capacitor will be transparent. So you have a behavior which is of this kind here. All right, you have a behavior of this kind, and one can do a similar analysis and find out what is the 3 dB cutoff frequency for this. And it's again simply equal to 1 by 2 pi RC. All right, so again, one can look at the transient response and define. So let me skip these things here. Now, so that was one single RC, either a low pass or a high pass behavior. Rarely would you find circuits which just consist of one R and a 1C. Even these are slightly uncommon, where you have one capacitor and many resistors in the circuit. And these are also easy to handle. If you have one capacitor and one resistor, all that you need to do is take this particular, whatever all that resistive circuit is there, apply Thevenin's theorem, and you can transform it into a single resistor, single capacitor circuit, and thereby you can find out what is R equivalent and get 1 over 2 pi R equivalency. All right, so you can get the cutoff frequency for one single capacitor circuits in a straightforward manner by converting the rest of the circuit into Thevenin's equivalent. Okay, and so all it involves is calculation of R Thevenin or R equivalent for this particular one. Okay, so any linear circuit, take take a Thevenin's equivalent, calculate R equivalent, and calculate as 3 dB. How do we know if the capacitor causes high or a low pass behavior? All right, here is a transistor now. Here is our amplifier, common emitter amplifier. And we've given you all for the time being, as I said, I've ignored all the transistor capacitances because we said that results in high frequency behavior. So we are looking at low frequency behavior here. And can you see that all of them result in this high pass behavior? This is a high pass behavior, right? High pass behavior means it passes all the higher frequencies and begins to attenuate the lower frequencies here. Can we see that all the capacitors act in that particular manner? All the capacitors that you see here? CB, low frequency, what will it do? Block. At low frequencies, the impedance of the capacitor is high, so it blocks the signal. And if the signal cannot travel through, obviously I won't get V0. Okay, so this acts to block, so we know it will result in this kind of a behavior. Look at this CC here. This will also at very low frequency block the signal here. It will not be able to reach the output, and that also results in this kind of a behavior here. What about this one? Does it also result in this behavior? That's not so apparent. But remember, at low frequencies, what will happen to this capacitor? Very, very low frequencies. Capacitor is like, the impedance of the capacitor is much higher than the resistor. So you can ignore the capacitor here, and then you get an emitter resistance in the bipolar transistor. An emitter resistance, when you get, you know that emitter resistance causes a decrease in the gain. On the other hand, when you go to higher frequencies, the capacitor acts as a short, and therefore this point becomes a small signal ground, and the gain increases here. So what you find is, again, you get a behavior like this here. At low frequencies, gain is smaller, and at high frequencies, when this acts as a short, the gain is higher here. So again, you get a behavior of this particular kind here. So all these three capacitors that you see here, CB, CE, and CC, they all result in this kind of a behavior here. Okay, which means that they all affect my lower cutoff frequency. So now the issue is, I have three capacitors and several resistors and dependent current sources and all that. How do I figure out what is my interest is in knowing the 3 dB cutoff frequency. So one approach is that I could, a general approach is I could write V0 by Vs. Right? Replace all the capacitors by their impedance, which is 1 over j omega C, and 1 over j omega CE, 1 over j omega CC, and it then becomes a circuit, a linear circuit. Analyze it using node, mesh, whatever you want, write down V0 by Vs. We'll call that as the transfer function. So that will be as a function of frequency. Well, I didn't have the patience to do that, but as I said, there are programs which will do it for you. They'll calculate V0 by Vs for you. And the program, one of the program gives this, the transfer function. This is a transfer function. S squared, S cubed, and all of that you see here. Okay? That's your transfer function. Okay? Transfer function for this circuit here with CB, CE, and CC here. Right? So the program, of course, doesn't care whether R pi is large or small or whatever. It takes a general approach and gives you this here. So note that I have the transfer function. In principle, I can calculate the transfer function. I have S squared and S cubed, and this is the constant term here. Then there is an S term, there's an S squared, and there's an S cubed. Right? I have a new transfer function available. And if you have the transfer function available, in principle, what can you do? You can plot it out and find out where the function drops by 3 dB and calculate. Except that I don't think I can get an expression for 3 dB from here. I mean, I can take this function and plot it numerically and find out where the 3 dB point is, but I don't think I can get an expression from here. Okay? So this approach, it fails. A general approach of writing a transfer function and plotting it out fails here. Well, we can simplify it. We can neglect a few things. Even then, it becomes there's a S square here and S cube here and all that. Still, it's complicated. We can simplify even further. But let's look at a different approach. The different approach is simplified approach, which is simple but not that accurate. What it does is it tries to calculate the impact of each capacitor independently. All right. So the idea is as follows. The idea is that you take this particular capacitor here. Okay. And you say this capacitor is the one, let's assume, that determines my 3 dB frequency. And the other capacitors, they have no impact. This is the most important capacitor, let's say. So when I say this capacitor affects my 3 dB frequency, then what do I do to this capacitor? And what do I do to this capacitor? I'm saying they are not having an impact on 3 dB. At this point, when I'm calculating 3 dB, this capacitor does not have an impact. And this capacitor does not have an impact. What should I do to them? Should I open them? Should I short them? They don't have an impact. So I should short them. I should short this particular capacitor and I should short this particular capacitor here. So I short it and I short it and I'm saying these are not having an impact on my circuit. My 3 dB frequency, remember, in this region, all of them are shorts anyway. In the midband, this is a short, this is a short, and this is a short. In the midband, all of them are shorts, approximately shorts, right? So they are shorts. So now as I approach here, I'm saying the first capacitor that begins to cause my gain to decrease is this one, let's say. Which means the others remain shorts. Okay? And so now if I remove CC, which means I short CC and I short CE, I'm left with one single capacitor here. And with one single capacitor now, I can determine what the 3 dB frequency is. Right? We've already seen one single capacitor means all you have to do is find out in series with this capacitor what is the equivalent resistance here. Equivalent resistance of all this here, and if I find it out, then I can find out what is the 3 dB frequency due to CV. Similarly now, next I make a hypothesis and say, well, this is the dominant capacitor here. So I keep this short and I keep this short and I determine a 3 dB frequency here, a second 3 dB frequency. Then I say this is short and this is short and this is the dominant one. And I determine the third 3 dB frequency here. Now suppose I determine 3 dB frequencies. One of them, let's say, is 10 hertz. Another one of them is 20 hertz. And the third one of them is 1 kilohertz. 10 hertz, 20 hertz, and 1 kilohertz. What do you think will be the 3 dB? 10, 20, 1 kilohertz. What will be the actual 3 dB? Very close to what? See, when this says it starts falling at 1 kilohertz. This says starts falling at 10 hertz. So which will determine? 1 kilohertz. So your 3 dB frequency will be 1 kilohertz. So the point is that when you calculate this 3 dB, this 3 dB, and this 3 dB, and you find one of them is dominant. One of them is dominant, which means one 3 dB frequency is 4, 5, maybe a factor of 10 larger than this 3 dB frequency and this 3 dB frequency. Then this particular one becomes your approximate value of the of your 3 dB frequencies. And it so happens that when you do the calculation, you find that most of the time, you know, if I use this as a 10 microfarad capacitor, this as a 10 microfarad capacitor, this as a 10 microfarad capacitor, I find one of the frequencies is indeed dominant. And therefore the method works fine here. So in general, this method that I'm talking about, I'm not going into the details of it, is called the short circuit time constant approach. So what it says is, what I just described, consider one capacitor at a time, assuming that it plays a dominant role and short circuiting the remaining. Compute the equal time constant and 3 dB frequency due to each capacitor. Determine this for each one of them. If one of the 3 dB frequencies is larger by a factor of, factor of 4 or 5 and all that depends on how accurately you want to calculate the final value. Okay, so don't pay too much attention to 4 and all that. If one of the 3 dB frequencies is larger by a sufficient factor compared to others, we take this as the 3 dB frequency of the circuit. On the other hand, if this is not true, if you find that the 3 dB frequencies are comparable, what we do is we add up all the time constants. So we add up all the 1 over 2 pi, 1 over time constant, and we say that's the 3 dB frequency. These are approximate methods for estimating. I will not say calculating the exact value, for a quick estimation of what the 3 dB frequency of the amplifier is. If you want an exact value, you'll have to go to simulation. Okay? There are others, you know that from your exposure to EE200 that you not only have poles, but you have zeros also. And there are better formulas which help you to calculate the 3 dB frequency here. But the picture or the method that we'll use is basically calculate due to all of them, due to each capacitor. And if one of them is dominant, take that as the 3 dB. If not, then add them up in an inverse manner. Okay. Upper cutoff frequency. Let's look at the upper cutoff frequency here. So here is our a picture for the entire amplifier here. Entire amplifier. Now note that we said that this capacitor, and this capacitor result in lower cutoff frequency. The transistor capacitances, which is here and here, they result in the upper cutoff frequency here. Okay, they result in this particular part here. So in general, what you find is that you have in a circuit, you have lots of capacitors that are there. Here we find 3 plus, we have 3 plus 2. Okay, 5 capacitors here. I've not drawn the, 3 plus 3. 6 capacitors are there. Right? Some of the capacitors you find, they determine this behavior, as we said. And some of the capacitors, they determine this particular behavior here. So in a general case, what I may have to do is, if I have lots of capacitors in my circuit, I need to classify them into 2 parts. Those that result in high pass behavior. This is a high pass behavior here. Note that this is a high pass. It attenuates lower frequencies and passes higher frequencies here. So classify the capacitors into 2 parts, high pass and low pass. Those that cause this kind of a behavior here. They attenuate higher frequencies here. So that's a low pass here. And by looking at the circuit, one can tell, as we just saw, that the coupling capacitors, they cause high pass behavior here. And all the transistors' internal capacitances, we'll see, they cause the low pass behavior here. So we've taken the capacitors and we have taken them into 2 classes. Those that cause high pass behavior and those that cause low pass behavior. Now, when I am handling these, note that these capacitors here, when I'm looking at upper cutoff frequency here. Upper cutoff frequency, when I'm trying to calculate here, and I'm saying, this is the low pass behavior here, it arises from here. What do I do to all these capacitors? They're all shorts. Remember, all these capacitors are shorts here in the midband. They're all shorts, and as I keep on going, they keep on behaving as a short here. So when I'm calculating the upper cutoff frequency, all these capacitors are shorts. That's what we've been doing in mid-band range. We've been shorting the coupling capacitor here, this capacitor here, and this capacitor. Okay? So these are all shorts here when I'm looking at this effect here. On the other hand, when I'm calculating this one here, all these capacitors are open. They're all open here. They're all open. They're open here. They're open, here. And they're open throughout. These capacitors here. Okay? All right. So for the upper cutoff frequency then, which is arising from C pi, C mu, and CCS here, our approach is the following. Again, we consider one capacitor at a time, assuming that it plays a dominant role, and we open circuit the remaining. We calculate the 3 dB frequency due to each capacitor, and if one of the 3 dB frequencies is smaller by a factor of 4 or so compared to others, we take this as the 3 dB frequency of the circuit. If not, we simply add up the time constants due to all the capacitors here, and we take that as the upper cutoff frequency. So these are simplified procedures. There is a logic behind it. I'll try and pass a reference which talks more about why this can be a reasonable approximation. I'm not going into the details here. All right, let's actually apply this particular method here. So let's take this. This is an arbitrary circuit, and we would like to calculate the lower cutoff frequency and the upper cutoff frequency for this circuit here. So we have V0 is our output. So if I plot V0 divided by Vin, I will get the standard plot of gain which falls at lower frequencies and falls at higher frequencies here. So we'd like to find out what is the 3 dB cutoff frequency. Okay? This is not an amplifier. This is a normal RC circuit here, but multiple capacitors are there. Multiple resistors are there. So remember what our approach is? We would like to classify the capacitors into those that cause high pass behavior and those that cause low pass behavior. Which are the ones that cause high pass behavior? High pass behavior means at higher frequencies, those capacitors don't matter. At lower frequencies, they matter. Okay? So which one will cause a high pass behavior? C1 and C3, everybody sees? C1. Note that at low frequencies, what will C1 do? C1 will be very high impedance, will block the flow of this particular signal to the output here. So C1 is blocking at high frequencies. At low frequencies, it causes a high pass behavior. Similarly, you can see C3. C1 and C3 cause a high pass behavior, and C2 and C4, they cause a low pass behavior. At high frequencies, what will C2 do? High frequencies, the C2 will act as a short, so this point will become ground, and the signal will again no longer appear here. Similarly, at high frequency, C4 will act as a short, the signal will no longer appear here. So all of them are causing a low pass behavior here. Low pass, which means at high frequencies, the output is very small. So I can take these C1, C2, C3, C4 and classify them into these two parts here. Now, what I do is, for lower cutoff frequency, what I'll do is C2 and C4, I'll keep it open. I'll keep this open, I'll keep this open, remove it from the circuit. Okay? So we are left, when you remove C2 and C4, you are left with this circuit. Now we said, due to each capacitor, find out the time constant. So we take C1. Once we take C1, what do we do? Consider C1 first. We short the, C3. We short the C3 capacitor here. So when I'm calculating the 3 dB frequency due to C1, short C3 here. So that's what I'm doing here. And then, of course, do the calculation after your transformation. I'm not going to go through that. So we calculate F1. When you look at C3, short C1. Short it here. Now due to C3, calculate the 3 dB frequency here. Find out what is R equivalent, find out the time constant, find out the frequency here. So we have two frequencies, F1 and F3. Let's take typical values. Suppose I put 1K, there's nothing typical about it, but let's take some values. 1K, C1, C3, C2, C4, some values here. And I'm not going through the details here. So we calculate F1 turns out to be 95.3. F3 turns out to be 6.36. So what will be our lower cutoff frequency? This frequency note is several times higher than this one. So FL is basically equal to F1. Lower cutoff frequency is 95.3. So in this case, we were very fortunate that the two frequencies are fairly far apart. So there's not much error involved. We can simply take this as the lower cutoff frequency. And when I actually do a simulation, so this is a simplified procedure. When I actually do a simulation, you can see our method gives 95.3. The actual method in simulation gives 103.0, which does all the detail analysis, doesn't make any approximation, gives us 103. So 95.3 and 103, we're quite happy with it. So, we're not looking for very accurate answers here. We're looking for, I'm getting an expression. So I'm finding that lower cutoff frequency is determined by F1. And I know an expression. So, and from R equivalent, I can identify which are the important factors which determine the 3 dB frequency here. Okay. All right. For the upper cutoff frequency, all the high pass capacitors are first shorted, C1 and C3. We take C1 and C3, all those high pass capacitors are shorted here. Then we take each capacitor at a time. We take C2 and then we open circuit the other one. And then we take this one and then we open circuit this one here. So consider C2 first, open circuit this one, calculate your R equivalent, time constants, 3 dB frequency. Consider C4 next. Then this one is open circuit. Calculate again all the R equivalent. Calculate the time constant. Calculate the frequency. So we have two frequencies. Let's plug in the numbers. 0.4 nanosecond. It gives us 0.39 gigahertz. 0.8 nanosecond gives us 0.2 gigahertz. We are in a little bit of trouble, right? One of the frequencies is not dominant. This is 0.2 and this is only 0.4. So I can't simply go ahead and say, well, let's choose 0.2. So what do? Well, since no frequency is dominant, so what I do is this time constant tau 2 and this time constant tau 4, we just sum it up. We say, well, both of them are important. So we calculate a effective time constant, which is the sum of these two time constants. Okay, we add up the time constants and we get 0.13 gigahertz. All right, how good is this approach? Well, we do circuit simulation. If I do circuit simulation and I calculate 3 dB frequency, what do I find? 0.154. 0.154 gigahertz is the actual 3 dB frequency, and our approximate method gives us 0.13 gigahertz. Again, not bad. there are errors involved, but note that the procedures are simple. Procedures are simple, and I will get an analytical expression. I know what is F2, what is this equivalent resistance here, what is this equivalent resistance here. So I get an analytical expression which will help me understand what the upper cutoff frequency is. What does it depend on? Okay? Yes? Which one? This one was less? Oh, less than the lower cutoff frequency. Those don't happen. That's what I'm trying to tell you. We are discussing a very specific, all this discussion is in a specific context of amplifiers. In amplifiers, we said that all those capacitors that you see here, these capacitors are all in microfarads. The transistor capacitances are all in picofarads. So yes, in general, if you say, well, it can happen. If I had an arbitrary choice of capacitors, yes, this C2, if I put these capacitors in picofarads and these capacitors in microfarads, yes, those kinds of things happen, but not for the amplifiers. Okay. All right. So that's the procedure then. So procedure again, let's come back to our original amplifier. This is a general amplifier, right? Here, even this is not here. Well, I don't have a general one. So let's come back then to lower cutoff frequency calculation here. Okay. So lower cutoff frequency, if you recall, what we'll do is all transistor capacitances will be open circuited. All transistor capacitances will be open circuited, and now while we do the lower cutoff frequency calculation, we've been saying that these results are useful results. We, from henceforth, unless we are forced to, I don't want to draw a hybrid pi model and then look at circuit analysis at that level. I would like to use these results, that when I look into the base, my resistance is R pi, and anything in the emitter gets multiplied by beta here. If you want, you can keep 1, but most of the time we'll neglect it. When you take a case like this and when you look into the emitter, then the resistance that you see here is R pi plus RB, the whole thing gets divided by beta here. Or if you have a simple case like this and you look into the collector, it's again a resistor which is very high R naught here. So these are, and there are other results as well, but these are, I could have put a resistor here also, and we have expression for that. Okay. Let me skip all these here. All right, so let's come back to our amplifier. We want to find out is 3 dB lower cutoff frequency for this particular amplifier. Okay, so the first step is take this amplifier, transform it into a small signal equivalent circuit. So VCC is to ground, and keep everything else. We are not going to replace by hybrid pi. Keep the transistor as it is. Okay, as it is here. And any of the resistors, we know R1 comes down, so R1 is in parallel with R2. We're going to keep all the capacitors. Our goal is to find out the 3 dB frequency. So capacitor, I'm not going to short now. This will not be shorted, this will not be shorted, this will not be shorted. Okay, so 3 capacitors are there. Our procedure is, let's calculate 3 dB frequency due to each capacitor. Due to this one, due to this one, and due to this one. And while we do that, while I'm calculating due to CB, I'm going to short the other ones. Okay, so that's what I'll do. So I'm calculating due to CB, and I shorted the other one. Shorted here and shorted the other capacitor. Now, what is it that we are calculating? we're calculating 3 dB frequency. And what is 3 dB frequency? Well, this is the capacitor. We are asking what is the net resistance that this capacitor sees. Net resistance with this capacitor here. So how do I find that out? Well, this capacitor, of course, if I look left, I see RS. If I look right, what do I see? What resistance do I see? What do I see? I see R1 parallel R2. And I see a resistance between base and emitter. And what is that resistor? R pi. So what is it? When I look from here, what is the resistance that I'm seeing? R1 parallel R2 parallel R pi. So what is my 3 dB frequency then? So this is the net resistance here. What is my 3 dB frequency? Would be the net resistance that my capacitor sees is on the left is RS, on the right is R pi parallel R1 parallel R2. And my frequency then becomes 1 over 2 pi CV, this much. That's the 3 dB frequency due to this capacitor here. Okay? Alright. Let's go to the next one. Now when I calculate due to this capacitor here, I keep the others shorts. So we have it here. And what is the net resistance seen by this one? Well, when I see from here, what do I see? Into the collector. When I look into the collector, note that's why I drew this here. When you look into the collector of a transistor, when you look into the collector, there's no source attached here. It's simply a resistor which is R0, which is a large resistor here. Okay? So what happens is, when I look here is R0. So this R0, when I look into the collector is R0, what does it mean? Is between the collector node and ground. Okay? So R0 will come in parallel with RC. And R0 parallel RC. And as I've been saying, in most of these circuits, RC is much smaller than R0. So we'll just take it as RC here. If you want to do more accurate calculation, you can do that. No problem. The net resistance seen by capacitor is then RC plus RL. And we can calculate the 3 dB frequency, which is 1 by 2 pi cc RC plus R. Alright. So that's with the second capacitor. Third one is here. So we want to find out what is the net resistance seen by this capacitor. Let me redraw the circuit. RC, we've combined RC parallel RL, this R1 parallel R2 with RS, we've combined them together, and we are asking what is the net resistance seen by CE. So in this case, what is the net resistance that I see here when I look into the emitter? We said the net resistance that you see when you look into the emitter is R pi plus the resistance in the base divided by beta. R pi plus RS parallel R1 parallel R2 divided by 1 plus beta. So the net resistance that my capacitor sees is RE. RE, of course, it sees, and in parallel with RE, it sees all this here. And my 3 dB frequency becomes 1 by 2 pi CE R equivalent. So I have now three of them, three frequencies. And if one of them is dominant, then I'm fine. I just choose that one, the dominant one. If not, then we add them up. So let's look at this particular example here. Okay, we've chosen 10, 10, 10. All right, so let's, ICQ is 3.48. R pi, do the calculation, 0.74. GM is 0.13. AV is 147.5. If I calculate due to this capacitor, it comes out to be 24.4. If I calculate due to this capacitor, 3.6 hertz. If I calculate due to this one, any guesses? Larger or smaller? .18 kilohertz. And therefore, my lower cutoff frequency is simply this, 2.18 kilohertz. Okay? And when I actually go and do the simulation of this one, I find 2.039. And the actual value is R value is 2.18, the actual value is 2.03. Pretty close to what we've just calculated here. This brings out a very important point now here. See, I connected 10 here and 10 here and 10 here. All the capacitors are the same. All the capacitors are the same. The highest 3 dB frequency comes out because of this one, because of this. So if you had a choice of, I gave you only 100 microfarad capacitor, and I said you can have only 100 microfarad capacitor, any number of 10, not any number, 10 microfarad capacitors. How would you distribute them? 100 microfarad capacitor and 10 microfarad capacitors. Where would you use them? Where would you employ them in your amplifier? Where would you use the 100 microfarad? Emitter, right? Because what is it that we are looking for? We are looking for FL. What do I want from FL? We want FL to be as low as possible. We want to extend the range over which our amplifier will work. So I want FL to be as low as possible. How do I make FL as low as possible? You saw that all the Fs, all the frequencies are 1 over 2 pi capacitor value and some resistor. So the larger the value of capacitor that you use, the smaller the F it gets. But what is the problem with large capacitor? Why am I using 10 microfarad? Why don't I use 1 farad? Huh? Why do I not use 1 farad capacitor? Have you seen a 100 microfarad capacitor in the lab? Huh? Okay, maybe next time I'll bring a 100 microfarad capacitor, and then you can think about what would a 1 farad capacitor look like. I mean, you know, capacitors are, the value of a capacitor goes directly with the area, right? Capacitors is area by whatever. So if 100 microfarad capacitors are pretty big, then a 1 farad capacitor would be huge. Okay, so you can't use that. You can't use very large capacitors here. Okay, and so this is the critical part here, as you can see here. This is the one which is determining your 3 dB, lower 3 dB cutoff frequency here. Unless, of course, you know, we can give you an amplifier where I've used 100 microfarad here, 100 or 200 microfarad here, and very low values here. 1 microfarad here and 1 microfarad here. It may turn out to be that this or this may become the dominant one. Okay? All right, so that's what we are saying. Typically, this is the expression for FB. What is FB? FB is due to this capacitor here. FE is due to this capacitor here, and FC is due to this capacitor. So we have 3 cutoff frequencies. FB is over here, FC is here, and FE is here. And what we are saying is, in most of the cases, it is this one which will determine your 3 dB cutoff frequency, FE. All right. So, you know, at times people have asked, for example, let's say if you are doing a design problem and this capacitor value is not given to you, this is also not given to you, and this is also not given to you, right? And you have to choose now the capacitor value. And suppose I say my amplifier has to work from 1 kilohertz onwards. My amplifier has to amplify from the signal that I'm going to amplify will contain frequencies from 1 kilohertz to some higher values here. What does that tell you? The amplifier has to amplify from 1 kilohertz, any frequency larger than 1 kilohertz. What does that tell you? What will you say should your 3 dB frequency of this amplifier be? Lower cutoff 3 dB frequency, which should be how much? If it's 1 kilohertz, less than 1 kilohertz, I don't know, maybe you can, looking at this kind of a behavior, maybe you'll try 200 hertz or something like that. So you know that then I should have my 3 dB frequency, which is maybe 200 hertz or so. So once you know that my 3 dB frequency is 200 hertz, okay, you've made a choice that 3 dB frequency is 200 hertz. How would you go ahead and choose this and this and this? These capacitor values. What do I have to do? Let's focus on this one. What do I have to do? I know my 3 dB frequency is 200 hertz. Now, how should I choose my capacitor here? Well, what is the 3 dB frequency due to this capacitor here? We have an expression, right? We have an expression. Let's go back to that one here. We have an expression. FB is here due to this. and I'm saying my 3 dB frequency should be 200 hertz. What should be the constraint on FB? FB should be larger than 200 hertz or smaller than 200 hertz? Huh? Smaller than 200 hertz. So you know that FB, so when I'm talking about cutoff frequency being 200 hertz, you would like FB to be smaller than 200 hertz. All right. You've already designed your amplifier in the sense that bias currents and all that have all been chosen. So you know RS, RPi, R1, R2, everything is, you know. And then once you make a choice of FB, maybe you choose it to be 50 hertz or whatever, and then you can determine the value of the capacitor that you would like to have. So that's how you go ahead and choose the value of the capacitor CB here. Similarly, how do I choose the value of capacitor CC here? Well, I go ahead and look at this expression. And I know that I'm looking for 3 dB frequency, which is 200 hertz. So again, make a choice of what you want FC to be. Maybe 20 hertz or 40 hertz or whatever. Make that choice. Smaller, considerably smaller than your 3 dB frequency. And that will allow you to calculate what is the value of this coupling capacitor, CC here. And similarly, lastly, go ahead and look at this expression here. And now, when you say 200 hertz, well, maybe we can set this frequency as roughly 200 hertz. This has 200 hertz. And we know all these resistors and all that are there. We already know their value here. And that would allow you to calculate what's the value of the capacitor here. Remember, our overall goal is that we don't want to use very large capacitors. Because they make, large capacitors means that they make the circuit bulky. And, it occupies more area, and we don't want to do that here. Okay. So you can set FE as 200 hertz, and from there then calculate what is the value of the capacitor that you want here. So that tells you now how to choose CE, CB, CC. All these capacitors, how do you choose? Okay. The next part is, so you have a choice of CE, of course, but you have a choice of R equivalent E also for affecting your 3 dB frequency. Suppose I tell you that I want 200 hertz 3 dB frequency, and you cannot use a capacitor which is larger than 100 microfarad. You can't use a capacitor larger than 100 microfarad, and I'm looking for 200 hertz. Well, if you put 200 hertz here, the largest capacitor that you can use is 100 microfarad. So that puts a constraint on R equivalent here. What kind of R equivalent do I have? And what does R equivalent depend on? It depends on R pi, RS, R1 parallel R2 divided by 1 plus beta here. So are you seeing a trade-off between, let's say, 3 dB frequency and something else? We've already seen that in an amplifier, what is important is voltage gain, input resistance, output resistance, voltage swing, stability. Well, now we are seeing one more thing, which is the 3 dB frequency. We would like 3 dB frequency to be as low as possible here. So let's take a case where, let's say RS that you see here, the resistance of the source is very small. RS is very small. So if RS is very small, know that RS is very small, which means that this term is negligible. Okay. So what we are left with is R pi by beta. Neglect 1 also. So you're left with R pi by beta. What is R pi by beta? R pi by beta is 1 over GM, and which is what? VT by ICQ, right? And let's say this resistor RE is large. Okay, it's 1K, and VT by ICQ, you know, is a small resistor. VT is 26 millivolt, ICQ is 1 milliampere, so VT by ICQ is 26 ohm. Okay, so we are talking about a resistor which is 26 ohm here, in parallel with maybe a resistor which is 1K. So we can forget about RE also. So you're talking about this whole resistor R equivalent being basically VT by ICQ. So now, what do you want from R pi by beta? VT by ICQ, you want to be large or small? To make upper cutoff frequency small. What do you want it from here? You want large, right? VT by ICQ large. Now, how will you make VT by ICQ large? VT is fixed. So what do you have to do to ICQ? Reduce. Right? You'll have to reduce the value of ICQ. Now, do you know that anything else depends on ICQ? What does gain depend on? Gain is ICQ times RC divided by Vt. So are you saying that if you try to get a lower cutoff frequency, which is very low, you'll have to make ICQ maybe large, ICQ small, and ICQ small may affect the kind of gain that you will get. So you will find that your 3 dB frequencies are linked to other parameters. And you might have heard this famous phrase that there is usually a gain bandwidth trade-off. Gain versus frequency trade-off here. And maybe you are seeing a part of it here. That if you try to push your lower cutoff frequency really low, you'll have to make this R pi to be high, which will require lower values of ICQ, and lower values of ICQ may impact your gain. Okay? So you're seeing that there may be a gain versus bandwidth trade-off here. So this is lower cutoff frequency. So what I've given you is that now the procedure is very general. Any circuit that you're given to and you have to calculate lower cutoff frequency, do it one capacitor at a time, find out the time constants, and then one of them is dominant, that's the lower cutoff frequency. If not, combine all the terms. Okay? All right, so let's stop here.